So it's a great pleasure to introduce Tina, who holds a master's in science in geology, actually igneous petrology, from Aarhus University of Denmark. Her oil and gas career path started with mudlogging operations offshore Denmark, and she worked for more than 20 years in Dong Energy, mainly in exploration projects in Northwest Europe. Some of her core competencies include play screening, seismic interpretation, and seismic stratigraphy combined with sedimentology, prospect evaluation, and maturation, including volumetric estimates and risk assessment. And these are, as I stated, her technical competencies and help to form her holistic view of the subsurface. Tina is currently working as an exploration advisor for WellPerform, and her technical responsibility includes play screening for both geothermal and oil and gas themes. The title of her talk today is Geothermal Play Area Mapping, a case story from Alabama, Mississippi, and Georgia, the United States. With that, Tina, it's all yours, and thank you for agreeing to be our speaker today.
Thank you very much for the introduction. I think it covers quite well for my career over the last 20-25 years. So I'll go straight to the presentation, and the outline of the presentation is here. I will start out with what is play area mapping and what can it be used for. It's something that I've been working with quite a good amount of my time in my former career, and maybe not all of you know what it is and what it can be used for. After that, I'll continue with the case story about the geothermal potential in Mississippi, Alabama, and Georgia, and I'll touch on data mining, the play maps, the composite common risk segment maps, and conclusions. And then I'll end the presentation with how can play area mapping support the decision-making processes. So I'll start out with what is play area mapping and what can it be used for. The play area mapping, it's a well-known tool for the oil and gas exploration and has been used for quite some decades. On the right hand side here, you can see what we call a play-based exploration pyramid used in the oil and gas business, where we focus on the basin at the base, then you continue into play focus, and finally the prospect focus. Along this, we have some decision gates, and also some of the things that you need to do to go from one level to the next level. Of course, this is different in the geothermal system, but some of the things will still be of great value. For instance, data mining and doing the framework, looking at the geology in a broad scale, looking into the reservoirs, and that can continue in, or the time frame for that will be days to weeks, or can be days to weeks. Whereas if you go a step higher up, looking more specific into play focus areas where it's more local things that you need to look into, it will take months because you need more details. You can do the same pyramid for the geothermal potential and actually also for CO2 storage. What the play area mapping does is it defines trends in a consistent way with the same conditions and adds a chance of success, the probability, to these mapped play segments. And I'll come back to what these play segments are. But the trends and the consistent way is actually the whole idea about the play area mapping. The play area mapping can also be conducted either at a high level, it could be countries, states, provinces, or at a much smaller scale where you look into counties or even a more local minor scale. The thing is that you have to adjust the amount of data you bring in for the high level compared to what you do for the smaller scale. You will most likely not take in a lot of details into the high level because the maps will not give you the right information. So I'll just bring on the play screening, mapping of potential areas to tell you a little bit about what the play screening actually is. For those who do not know it, we bring in different elements, and this is an example I've made where we look at reservoir facies maps, top reservoir structure maps, temperature maps, top seal maps, and database maps. And this play screening is set up for the geothermal evaluation. Then we do what we call a common risk segment map for each of these elements. That means that the reservoir facies maps, it gets some colors on, and the colors relate to a chance of success table that we have over here, with red being 0 chance of success, and the green one is the probability of 1 or 100% success, chance of success. So you start out making all these individual common risk segment maps, and for instance here you can see you have a yellow and you have a green, and each of these segments are what we call play segments. After having looked at these individual elements, you can do a multiplication, and then you end up with what you can call the final map, or a composite common risk segment map. And that is the map that combines all the individual probabilities that you have assigned to each of these layers. For the study, or the case story that I'm going to present here, that is the composite common risk segment maps that we will show. This case story, mapping the geothermal potential in Mississippi, Alabama, and Georgia, it's a collaborative work between Well-Perform, Petrolern, and Southern Company. And the play area covers 3 states, as you can see here on your right hand. And it has been quite a large area to cover, more than 400,000 square kilometers. And sorry, I will be using the SI units, but on all the slides you will find miles and Fahrenheit and feet also. So when we started this play area mapping, we saw that covering such a large area, we had to do it at a high level. We started out framing the play types and selecting the elements, and set up the criteria for mapping out the geothermal potential. And after doing that, we applied the chance of success, what we call the COS, to the play segment maps. The data mining forms the base of the play screening, and it can contain any kind of data. It could be seismic data, it could be well data, which we didn't use in this case because the area was simply too large to be able to get any good results, and also within the time frame. Then you can use literature, reports, articles, whatever you can find of public data. You have to see if you can trace down some top reservoir and top seal depth maps to guide you at what depth your reservoir is located. If you have by any chance reservoir quality data, you most likely want those as well. And of course, because we're talking about the geothermal potential, some temperature data. Then you have to define the area of interest, and that could be any size. It has been different in this project here, using the geology, defining the area of interest, or it was based, or you can base it on the outline of the states. And what we did here was actually using the states and see how the geology fitted into that outline. As I said before, we had to home in on the plate types, defining those. And during the data mining, we saw that it would most likely be sediments and basement rocks. And for the sediments, it's the whole coastal plain province, both the Gulf and the Atlantic. And for the basement rocks, it was the Appalachian Mountains. For the top reservoir depth maps and for the top seal depth maps, we found some information that we could use in the USGS groundwater atlas reports, and we used some maps from the Cretaceous and deeper, and we have only been dealing with one seal above the Cretaceous, and because that was one of the regional seals that we saw, we could take from one state to the next. Of course, if we had just been doing individual states, it could have been maybe slightly different. And I'll come back to that because it all boils down to the geology in the area. Then we also used well cross sections from reports just to give an idea of the dip and the depth of the reservoirs we were looking at. Finally, we used some temperature data from NREL, which is a National Renewable Energy Laboratory. They have done some nice maps in a web GIS environment, so we were able to download those and use them. And they had done some screening of a lot of wells with 25 Celsius degrees intervals and 500 meters intervals. The roll-up or the composite common risk segment maps, we created two for Mississippi, containing the Cretaceous and the Jurassic. In Alabama, we also created two maps, both the Cretaceous, but it included the Jurassic and the basement play, and also the Jurassic. In Georgia, we ended up with one composite common risk segment map for the Cretaceous, which also included the Jurassic and basement play. And it'll become more clear when we see the composite common risk segment maps. I talked about the NREL temperature depth maps from this web GIS portal, and these maps, it's based on estimated bottom hole temperatures, which has been horizon corrected. And as I said just before, it is 25 degrees Celsius temperature intervals and 500 meters depth intervals. So when you look at the left-hand slide up here, or the figure out here, it's actually a depth slab at 500 meters. And then they have graded up the well temperatures, the bottom hole temperatures, So you can see you have an area here with 0 to 25 degrees Celsius. The Celsius or the degree Fahrenheit is down here. And in these two areas here, it's 25 to 50 degrees Celsius. So for each 500 meters, the next here is a depth slab of around 1,000 meters. And then it just continues all the way down to 3,000 meters. And down at this depth, you can see you have a corner to the northeast, which contains temperatures between 75 to 100 degrees Celsius. And down here to the south, it's 100 to 125 degrees Celsius, both in Mississippi, a small part of Alabama, and in the southern part of Georgia. So when we were looking at, when we were trying to frame or select the criteria, we looked at these temperatures and we agreed that 0 to 25 degrees, that's not really a temperature that you would go for in the geothermal. And I know in the US that there is a difference between what we call low and medium enthalpy compared to Northwest Europe. But we set the threshold at 50 degrees Celsius. And we also included the 25 to 50 degrees because looking at such a large area, there is some uncertainty, and also maybe some of the areas where you will be in this range, you can have 50 degrees in some places and maybe 25 in other places, but that would not be possible to screen out on this high level screening. Another important thing when you do the play area screening is to look at the geology. And here I put in a section of the geological map of North America. It's a USGS geological map with the subcrop units. And we focused on the sediments, and they comprised gravel, sandstone, claystone, carbonates. And most of them are related to fluvial to deltaic nearshore marine deposits, which means they have some sort of heterogeneity into the layers. So it can quite easily change from sandstone to more claystone when you're looking into the fluvial deltaic marine environments. We also looked at the basement and its basement sediments and igneous rocks. And for the igneous rocks, it will basically be fractures and joints that will create the reservoir in these rocks. The map here shows the Holocene to Cretaceous sediment package with the green to the orange yellow here to the south towards the Gulf of Mexico, and it's all sediments and in a broad term called the coastal plain province. It's layers that all dips towards the Gulf of Mexico, and they form quite a broad, accurate band along or around the Appalachian Mountains, which are located up here to the northeast. North in Alabama, we have the Carboniferous Highland Plateau, or the flatlands. It's also sediments, but because of the age, the reservoir quality is not as good as what we see down here to the south and the southwest. And then we have the Cambrian or older, the Appalachian Mountains, Valley and Ridge, Piedmont, what all the mountains are called over here, and it's the basement. So having a picture of these rock types will probably help you when you see the composite common risk segment maps. And the line between the sediments and the older part up here to the north east is called the fall line, and it's also indicated on the maps that we're going to see. But it's not only the subcrop map that is interesting, it's also getting an idea of what kind of formations do we have in these intervals. And here we use the USGS groundwater atlases, and we also took the terminology into the play screen because they talk about aquifer systems. And aquifer systems is a good term because when you're looking at this high level scale, you may have several formations within an aquifer system, but they can be hydraulically connected. And the reason for taking in the aquifer system terminology was that we saw this complexity of the stratigraphic units and the high level screening. So for instance, if we look here on the map, we can see that the Black Warrior River aquifer down here covering most of the Mississippi, Alabama, and Georgia, it consists of several groups, formations, and sandstones, and so forth up here in even the younger groups and sediments. But here we can actually see that we have the Selma group as a sealing or confining unit, and we have the Black Warrior River aquifer as the aquifer system that we have looked at. The aquifers can be lateral equivalents, as you can see here from the Max Shannon formations and Utah formations. And that can be they can be laterally or lateral equivalents between all three states, but the lithology and permeability of each aquifer can be quite different. That's something you would do in a more detailed screening, go into the different formations. But we will have the helicopter view in this this case story. So now we start looking at the play maps, and we will start out with the Mississippi play maps, and it says maps because we actually got two. The first one is the Cretaceous composite common risk segment map, as you see here to the right. We have put in the degrees Fahrenheit on the map, and here to the right we have a conversion between depth in meters and feet. So I'll just stick to what it says in the boxes, and hopefully you have time to just have a quick look to see what it is in feet or in Fahrenheit. I've also put down here the stratigraphy just to show you that this is the Mississippi, and we're looking at the Selma group and the Black Warrior aquifer system here in the Cretaceous, Upper Cretaceous and Lower Cretaceous. We were able to find a depth structure map, but only covering the northernmost part of, or the northern part of Mississippi. So the line hatched down here, we didn't have any depth structure map. So being a geologist, you have to be a bit creative. And what we did, we extrapolated temperatures and the depth lines from Alabama into Mississippi, and the highest confidence is in between the orange and the light green here, whereas down here between the light green and the dark green, the boundary here is a bit more uncertain, marked with these question marks. As I said, we were looking at the Black Warrior aquifer system, siliciclastic sediments, a lot of sand, and we had the Selma Group seal unit or confining unit with carbonate shales. And then we used the NREL temperature depth maps. So the red here is the red area up here has a chance of success of 0. And that's basically because the temperature is cold. It's between 0 to 25 degrees Celsius, 500 meters and shallower. So it wasn't a target for the study that we did. If we go further to the southwest, we're entering into a play segment, which these are called, where we have a temperature between 25 to 50 degrees Celsius at depth between 500 to 1,000 meters. We assigned a chance of success of 0.3. Going deeper, both the temperature increase and so does the chance of success. Now we are at 1,000 to 1,500 meters with temperatures around 50 to 75 degrees Celsius. So this was actually the threshold or the boundary, the barrier that we set that we were going to screen for temperatures higher than 50 degrees. But as I said previously, we also included this as having a chance of success of 0.3 because within this area there might be places where you can actually find temperatures of 50 degrees, but it needs more detailed screening. Then we get into the very nice dark green color here, having a high chance of success of 0.9. The temperature is now increased to between 75 to 100 degrees Celsius, and even higher temperatures down here to the southwest, where it's of course a bit more uncertain due to we didn't have the depth map, but the general trend and dip of all the sediments is going towards the Gulf of Mexico. So it's very unlikely that the temperatures and the depth is not increasing. So that was for the Cretaceous interval that we did the composite common risk segment map. And here is the Jurassic composite common risk segment map. Here in Mississippi, we didn't find any depth structure maps, but we were able to find a reservoir facies map within the AOI, the area of interest. And I didn't mention that before, that the area of interest for Mississippi is actually the state boundary, because all the sediments are present in there. That's not the case for the Jurassic. It's related to the Mississippian Salt Basin. It's relatively deep, but it has a high temperature. We were looking at the Norphlet Formation, which is a sandstone, with the Smackover-Haynesville Formation as sealing units comprising carbonate, mudstones, and evaporites. But as I said, the temperatures are quite good here, or at least they are higher than 50 degrees Celsius. And the depths are definitely also deeper than the 3,000 meters of the NREL maps. When we look at the facies, we can see that what we have assigned a green color here and a 0.7 of the chance of success. It's because we have Aeolian dune facies. It has got fair reservoir properties and good temperatures, higher than or 125 degrees Celsius or slightly higher, but the depth of 4,000 meters or deeper. One thing that you should bear in mind is that there is a difference when you are looking at oil in a reservoir and water in a reservoir. Some reservoirs, they can easily survive with the reservoir properties or the quality with respect to porosity and permeability, because the oil on early oil migration actually prevents diagenesis and cementation. That's not the case when you're talking about water. So the deeper you go, the more cemented the sands may be. Again, we need more details to see if this is actually the case, but there is a good potential here in the Aeolian dune fascias. If we go up north from that, we are entering into a different depositional environment, and that's covering alluvial fascias, poor reservoir properties because it's not so mature and well sorted sediments. The temperatures are still good, and the depths are now at 3,000 meters to approximately 4,000 meters, maybe deeper. The question marks put in here is basically because we didn't have any depth maps to indicate where we go from around 3,000 meters, or if some part of this could actually be as a very small segment over here close to Alabama, where we see that 1,500 meters and up to or down to 3,000 meters could be a potential area and segment to be in. Over here, it's 0.4, the chance of success, and it's extrapolated from Alabama, as I just said. Going deeper into the basin and the depositional environment, we are entering into possible marine fascias where you have more claystone. Again, your reservoir properties probably suffers from being so deeply buried, and also introducing more claystone. It has high temperatures and a depth of 4.5 kilometers or deeper. So because of the uncertainty and because of the depth, it has been put as 0.3 for the chance of success. Then we move to the next state, to Alabama. It's basically the same methodology that we have just I've just shown you for Mississippi. It's again the Cretaceous depth structure map that we're using. The area of interest is the whole state. We are looking at several plate types in this, and that is basically because the Cretaceous is not covering this part up here. That's the basement, and down here the Cretaceous is it has a chance of success of 0 because of the depth and the temperature. So we were looking into other parts in the southeast part of Alabama, and as you can see here, we have introduced the Triassic play because the red segment would just be covering the whole area over here. So we just went stratigraphically deeper to see what kind of sediments would you have then. And we entered into an area where we had the Triassic red beds and a small part down here which you don't really have a lot of deep wells, so it's just called the pre-Jurassic play, but it's a mixed lithologies of both Triassic and Carboniferous and Precambrian rocks. Again, I will start stratigraphically from the top. We are still within the Black Warrior River aquifer system here with the Selma group carbonate and shale units as a cap rock. And we can see we are again dipping towards the Gulf of Mexico, getting into warmer and warmer intervals, and also more and more green, nice colors with respect to the temperatures, or the combination of temperatures and the reservoirs. So it has been the same chances of success assigned, and here for the lower part it was slightly deeper in Alabama. Here it's said, 2,000 meters plus. When we look at the southeast area here with the Triassic play, you have a cold and not so interesting play segment with the cost of 0, and you're entering into areas where it becomes you have a higher chance of success, and the temperatures are increasing, and so the depth are also getting deeper. The Triassic play has a slightly lower chance of success, and that's basically because of the reservoir properties due to the sediment composition. The Triassic red beds has a really, or it can consist of a lot of different mineralogy, and also a mixture of immature and mature grains. To the north or the northeast, we have the basement play, and it's simply just looking at of what is just below the soil, and you're entering into the basement, and you have to drill pretty deep down to between 2.5 kilometers to 3 kilometers to entering into temperatures of interest, and that is the 50 to 75 degrees Celsius and 75 to 100 degrees Celsius. The light green is the coldest and the shallowest targets, whereas the dark green line shaded is deeper and warmer. And as I pointed out, here is the fall line, and we extrapolated the basement into this area because it was because of the Cretaceous was too cold. In Alabama, you also find the Northlet formation, and here we could combine both a depth structure map and also the fascias map for the Northlet formation. Again, as for Mississippi, it's the Smackover Haynesville formation seal units that we have for the sandstone, and also here temperatures are above 50 degrees Celsius. The Aeolian dune fascias with the fair reservoirs are located here to the southwest, and we have the alluvial fascias at depth of 3 kilometers to 4 kilometers in the orange color, and a slightly more positive area up here, still the alluvial fascias, but it's not as deep as this play segment here. So 0.3 is assigned to the orange, and 0.4 is assigned to the dark yellow segment. We also used the fascias maps, as you can see down here, but we also used a line, a well cross-section line running to from north to south, very close to the Mississippian-Alabama border. And the Northlet, we can see down here, it's quite deep buried, so there is a risk that the reservoir might have suffered. But again, we have to look into more details to get a good grip of how good or how bad it can be. And finally, we have the play map for Georgia. This is also a combined composite common risk segment maps, and that is because, as you can see here, we both have the basement play, we have the Triassic play, and we also have a Cretaceous play down here to the southeast. Again, we're looking at the Black Warrior aquifer system, this as with the siliciclastic sediments, the Selma group, and for the Triassic, it's the red beds and the basement in the Appalachian Mountains. Down here we can see the stratigraphy for Georgia. If we start out here with the Cretaceous play, we can see that the temperatures are now slightly less than they were in Alabama and in Mississippi. Now it's between 25 to 50 degrees Celsius at depth between 1,000 to 1,500 meters. So it has a cost of 0.3. It has the same cost as the Triassic, where you have the same temperature and the same depth. The Triassic, when you're going towards the southwest, it gets deeper, and the temperature increases to 50 to 75 degrees Celsius. So it's slightly higher here to the southwest than to the southeast. What you can also see is quite a large portion of Georgia. You have the basement play. And as for Alabama, you have an area where it's a light green shaded with a cost of 0.6 and a dark line shaded area with a cost of 0.8. And the basement play here is dependent on fault and fracture connectivity, as it is for in Alabama. And the temperatures are the same, 50 to 75 degrees up here to the north at 2.5 kilometers depth, and 75 to 100 degrees Celsius at 2.5 to 3 kilometers depth. So what we did was we merged the composite common risk segment maps, because that is what the whole essence is in doing the play maps. You can do individual area of interest plays, but as soon as you cross borders or the outlines of these area of interest, it should be seamless when you're looking at the geology, because geology doesn't follow any man-made borders. So this is the merged map for the Jurassic play covering Mississippi and Alabama. And here is the more complex composite common risk segment map merged with both Cretaceous, Triassic, and basement plays covering all 3 states. And when you look at these maps, the colors, they tell you a lot about not only the geology, but also the depth and the temperature that you would like to see or have an idea of where to explore for. Well, it was used in the oil and gas business, but you could do exactly the same for the geothermal business. So the conclusions on this case story is you have estimated highest temperature and depth relations in the sediments and the potential reservoirs. They are found here in Mississippi in the southwest and getting colder across Alabama and into Georgia. The highest temperatures 100 degrees to 125 degrees Celsius or higher, they are located in the Jurassic play in Mississippi and Alabama, at depth between 2.5 to 4.5 plus kilometers. And finally, you have the green shaded segments up here to the northeast in both Alabama and Georgia. This is the basement play, where you need to drill 2.5 to 3 kilometers deep to reach estimated temperatures of between 50 to 100 degrees Celsius. So this was the conclusions on the case story, and then you can ask, or I asked myself, how can I end this this presentation? And I think we started out with looking at the play area map and the how we do that. And I think it is, you can ask, how can this play area map support decision-making processes? It's nice colors on the map, yes, but what does it actually mean and how can you use it? So the maps, a map is a key tool for focusing the activities and also communicating a strategy, whether you're a private company or you're a big governmental institution, or it's about how you can convey your information. It reflects the geology or the geoscience in the area of interest. And these areas, they can be overlaid by non-geology, non-geoscience data and information for making further decisions. So for instance, you can go in and have a look at any old dry wells that you would like to look into, or license holders. It could be national forests you don't want to mess with if you're planning a geothermal plant and investigation or research. It can be a lot of different things that you can put on top of these geological maps, and that can help you both the communication and focusing the activities. In this case story, which I've just presented, the scope of work was to map out the geothermal potential within the 3 states, and basically the rock type, the quality, and the temperature depth. And this approach is now under consideration to determine geothermal play fairways in other parts of the US. So I think it's a valuable tool and message to give you that are listening into this presentation. And finally, the play area mapping methodology can also be adapted and used for CO2 storage by selecting appropriate elements and criteria for the screening. So thanks for your time. That's the end.
Tina, thank you very much